Finally, our third and last adjective for today, f is bijective. I'll also include this onto y part, but again, that's usually omitted if the context is clear, that f maps x to y, that y is the chosen codomain. So we'll say f is bijective onto y, if and only if, and then it's just the conjunction of number 1 and number 2. F is both injective, that's just something you can say about f, it's injective, period, and f is surjective onto y. So it's just a conjunction of both. So some quick examples. Here's our earlier example of a non-injective function. Okay, well that's not bijective because it's not injective. To be bijective, you have to be both. Let's see, this was our example of non-surjective function. So this f maps x to y, and it's not surjective. It missed out on getting b. So this would be not bijective, at least not bijective from x to y, because it misses out on b. But this is actually very not bijective, because it's also not injective, right? It's not injective and it's not surjective. So this is very much not a bijective function. Okay, so let's try to actually construct something that is bijective. So let's say x is x, y, and I'm not going to include z. Actually, let me include z, and let me enlarge capital Y. Let's make capital Y be A, B, C, like that. So this and this. And let me try to draw a picture of something that is bijective. And I'm not just going to cut to the drawing, I'm going to show you the process of drawing it if I'm trying to think of what rules I have to follow in order to draw something that is bijective. So first of all, it has to be a function. So I'm not allowed to do this, right? I'm not allowed to do this. So let me state clearly that what I want. Want f such that all three of these things, f maps x to y, f is injective, and f is surjective. And by surjective, I mean surjective onto y. So these two together mean f is bijective. So this is what I'm trying to draw, and I want you to see the process of drawing something like this. So f maps x to y, this can be guaranteed by just drawing any connection of edges from here to here, as long as it's a function, and so it's a function means I don't do things like this, where multiple arrows come out of the same place. And secondly, I have to make sure that everything from here gets some arrow coming out of it. So I cannot do something like this, send these over somewhere, and then leave something isolated with no arrow coming out of it, because if I did that, then the domain would not be x, right? So to have this first bullet point, those are the rules I'd have to follow. Now what about injectivity? So injectivity says, basically, I cannot do something like this, right? I cannot make two arrows come in to the same place, right? I cannot do this. That's injectivity. So injectivity says every dot here has no more than one green thing coming out of it. You cannot have 2 or 3. No more than one green line coming to every dot here. That's injectivity. Surjectivity says I can't leave someone here isolated with no green line. So no less than one. There has to be at least one green line. So you see how injectivity and surjectivity sort of say dual kind of things, related but opposite kind of things about the things in Y. Injectivity says each dot back over here has at most one line leading up to it. And surjectivity says each dot here has at least one line. At most, at least. And so together, bijectivity says that each dot here has exactly one line leading to it. That's bijectivity. And if I also want my picture to have the domain bx, then I'm sort of forced to, do things like this. So this is one choice. This is one choice of a bijection from capital X to capital Y. Sometimes, for, I hope, obvious reasons, a bijection is sometimes called a one-to-one correspondence between two sets. So a bijection from capital X to capital Y is called a one-to-one correspondence between the elements of X and the elements of Y. So everybody from here gets exactly one friend from there, and nobody on either side is left friendless. Another way I like to think about it is in terms of existence and uniqueness. So injectivity alone is kind of a uniqueness statement. It's saying for every element here, there's a which has somebody that maps to it. That somebody is unique, right? Like injectivity says, for example, about A, that there's not more than one thing back here that maps to A. So that's a uniqueness statement. Surjectivity is like an existence statement. It's saying everybody has at least one thing mapping to it. So for everything here, there exists something back there mapping to it. And in fact, this idea that surjectivity is an existence statement, you can see literally here in this thing that you'll do on your homework. The existence statement shows up. Now, quick comment about using this definition in practice. So I already mentioned to you that usually you would use the definition of injectivity directly rather than this criterion given here. It's just much more convenient to use this in most cases. For surjectivity, on the other hand, I would actually use Theorem 59 usually to prove surjectivity, except for when you're proving Theorem 59 itself. That's the one exception, obviously, but usually I wouldn't just use... you could use this, but sometimes it's kind of awkward. I find Theorem 59 to be a good way to go. So usually a proof that a function is surjective will start with, okay, consider any element of the codomain, y. And then the proof will proceed to attempt to find an x in the domain such that f of x equals y. So that's usually how a proof of surjectivity goes.